All right, so where we are now, we've done a few of these instantaneous rates of change problems, both thinking of it as instantaneous rate of change and also as the slope of a tangent line. Same process in either case, though. And now what we want to do is start looking at business and economics applications to these sorts of things. So to do that, I need to introduce some functions that are going to be showing up very frequently throughout this course. And these are shown here. So let me go ahead and give you the explanation. We've already talked about this function c of x. And remember, the role of that function is that you're thinking about a company or a manufacturer that produces some kind of product. If x is the number of units of their product that they produce, then c of x is how much it cost the company to produce that many units. But there's other values associated with this that we would care to know. One of which is the price. So companies produce products for the purpose of selling them to make a profit. And so they have to price their commodities, or they have to price their products in a way that's competitive and is going to earn them profit. So the price of a commodity depends on numerous different factors. But a lot of the time, one of those factors is how much a company assumes that they will sell. They can project some figures and make some predictions about how much of a product they expect to sell. And they can price their product based on those projections. So basically all that is to say is that oftentimes the price of a product is dependent on the amount that they sell, in which case we can write that as lowercase p of x. That's called the price function. Okay? When selling their product, the money that they earn is called revenue, and that revenue also is obviously dependent on how much they sell. So revenue, or the revenue function, we use a capital R of X, and that just tells me how much revenue the company makes by selling X products, or X units of their product. Finally, we have the, well, this is a typo, it should say profit, not product. We have what's called a profit function. And a profit function is exactly what it sounds like. It tells you the amount of profit that a company makes selling X units of their product. Profit you compute by taking the amount of money you have earned and subtracting the amount of money that you had to spend. So subtracting your expenses and your overheads and things like that. And whatever is left over from your revenue after deducting your cost is profit. Okay? So the relationship between some of these functions is given here. Revenue is equal to x times p of x. And that one, to make sense of that, your price function is specifically telling you what the price per unit is for whatever a unit of your product looks like. So if I'm selling, pens, for example, like this pen that I'm holding, and I'm charging 10 cents per pen or something like that, then P of X should be 10 cents. Even if X is like 100, I sell 100, of these pens, then I would have made $10 off of that. But the price function is only telling me the price per unit. It's 10 cents. Revenue is how much money I've made for selling those X products. So if this is the price per unit, I would have to multiply by the number of units that I sold to get the total amount of revenue. And that's where this is coming from. Profit, like we said, is the amount of revenue, how much you make, minus the expenses, which is C of X. That's the cost to the company. So you have to deduct that before you can see how much you actually get to take home, right? So all of those functions are going to be making appearances starting in this section, but like all throughout the rest of the course, because they help give context to the calculus that we're doing, but in like these, application problems. So here's an example. A tennis shoe company can sell X pairs of shoes at a price of P of X equals negative 0.002X plus $80 per pair. like we mentioned before, these functions, like for price and revenue and all these other things, we could teach an entirely different class on how to derive these functions with the given information that you would have within that company. That's not what our goal is for this course. Our goal is to use these functions after they've already been worked out in, other types of problems. So we're just going to take it on faith that this thing does what it says it does. The cost of manufacturing X pairs of shoes is C of X equals 35X plus 9,000. Find the instantaneous rate of change in profit when 10,000 pairs of shoes are sold, and then we want to interpret that answer. Okay, so I'm seeing the word instantaneous rate of change, and specifically in profit. So in order for us to make any sense of that at all, I need a profit function, and I'm not given a profit function anywhere. But we know that profit, P of X, is equal to revenue minus cost. And I do have a cost function. It's right here. I don't have a revenue function, though. So revenue, R of X, that's the other thing that we had to figure out on the previous page. It's X times P of X, lowercase p of X. So number of units sold times the price per unit. And I do have a lowercase p of X. It's right there. So this is going to look like X times negative 0.002X plus 80. And I'm going to distribute that X in so that I get negative 0.002X squared plus 80X right there. Okay. Now that I have this revenue function, I can use this up here. So revenue is negative 0.002X squared plus 80X minus my cost function. Make sure you're using parentheses. The cost function has more than one term in it, so without parentheses, you're not subtracting all of those terms like you should be. 35X plus 9,000. Distribute that minus sign and take a note of the fact that there's some terms to combine. So I'm going to have an 80X minus a 35X, which is 45X. That means that I have this, negative 0.002X squared plus 45X. Then the minus will be distributed to the 9,000 as well. So I have minus 9,000. So this right here is the function whose instantaneous rate of change I'm actually looking for. And I'm gonna do that down here. So now what we want is the limit as h goes to 0 of p. That's what our function is called now, so I'm not using an f anymore. P of what? Well, it says instantaneous rate of change in profit when 10,000 pairs of shoes are sold. That's the number that gets used here. 10,000 plus h minus p of 10,000 all over h. Okay, so let's go ahead and start plugging some things in and seeing how things simplify. So I have the limit as h goes to 0. Let's plug this in first. 10,000 plus h gets plugged into this function right here. So negative 0.002 10,000 plus h squared plus 45 times 10,000. I hope I left myself enough space here. Plus h plus, minus 9,000. Okay, I don't think I did leave myself enough space. I'll write it down here. Minus, okay. The next thing that we need is a profit evaluated at 10,000. So I'm plugging 10,000 in for x here. So minus negative 0.002 times 10,000 squared plus 45 times 10,000 minus 9,000. And all of that goes over h. All right, I probably should have written that over here so I had much more space to work with. I'll do that for my next one. All right, let's do this. Equals the limit as h goes to 0. Now there's a lot going on in here, and it's at this point that it helps to make some smart arithmetic, or use some smart arithmetic tricks. So a couple of things that I'm noticing. All of the stuff in parentheses here is being subtracted from all of the stuff up here. And up here, I have the same constant term showing up in two places. I have one here and one here, but I'm subtracting those. So this negative 9,000 and this negative 9,000 will cancel when I subtract them. So rather than try to, multiply things out, get all the constants added up and everything, I can right away see that those will cancel out. I kind of see another thing that's going to cancel out. Notice this 45 has to distribute to both of these terms, and I'm going to get 45 times 10,000 here. But I have another 45 times 10,000 right here, and again, when I distribute that minus sign, I'll be subtracting them from each other. So that is going to cancel with that. Okay, that's going to help with, simplifying all the junk that's going to come out of this stuff here. So let's see what else we can do. Negative 0.002. I'm going to have 10,000 squared here. So that's going to be 10,000 squared is 1 followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Boom, boom, 100 million, plus 20,000 h, plus h squared. Okay, moving on to what's next. I have this 45, but remember we canceled this 10,000 with this 10,000 here, so it's actually just plus 45h. And we've dealt with that negative 9,000, that's gone. I have minus... let's go ahead and distribute this minus in right here. So I'm going to get a plus here because it's minus a negative. 0.002 times 10,000 squared. Remember, that's 1 with 8 zeros. 4, 1, 2, 3, 4, comma, comma. And then this canceled and that canceled. So notice a lot of stuff is canceled out before I've even had to do any calculator work, which is helpful. Okay, now I need to distribute this negative 0.002 in, but I'm seeing something else that's going to be helpful. When I distribute it in here, I'm going to get negative 0.002 times 100 million, and over here I have a positive 0.002 times 100 million, which means that will end up canceling with this after distributing. So I don't really care what that equals because I can just see the cancellation happening there. What else do we have here? So I have the limit as h goes to 0 of what do we have? So when I multiply this to this, the decimal point is going to move us 3 units this way and then multiply a 2 there. So that's going to be negative, right? So we're going to have negative, what did I say? 4, 1, 2, 3, negative 40. So that's going to give me negative 40h. And then here, when I multiply to that h squared, I'm going to get minus 0.002 h squared plus 45h all over h. I see like terms. Those can be combined. This is equal to the limit as h goes to 0. That would just become 5h. Minus 0.002 h squared all over h. And now we've done so much work on this, I can see where it's all going. I can see what's going to cancel. So this h and this h cancel, but this also has to cancel with that guy, and I'm going to lose one of those h's, leaving me with the limit as h goes to 0 of 5 minus 0.002 h. Here is the final step, because I can plug that h or that 0 directly in for h. That term goes away. I get a 5. Okay? But this is an application problem. I don't want to just say 5. I want to think about what that is. What did I just find? It says find the instantaneous rate of change in profit when 10,000 pairs of shoes are sold. So profit, P of X, think of the input units and the output units, because remember, for rates of change, the units are output units over input units. The output units are dollars, because profit is measured in dollars. The input units are pairs of shoes, because that's what X represents, how many pairs of shoes were sold. So the rate of change is going to be $5 per pair of shoes. Okay? It also says to interpret your answer. So putting everything into context now, we're going to write a little sentence that interprets this. So when the company sells 10,000 pairs of shoes, okay? Remember, that's we needed that 10,000 to come up with this. That was used here. We get this rate of change. What this rate of change is telling me is that once I have sold about 10,000 pairs of shoes, right around that value, I would expect each new pair of shoes that I sell to generate $5 in profit, because this is a rate, so it applies to each pair of shoes that we sell after this point. So when the company sells 10,000 pairs of shoes, they will make $5 in profit for each pair of shoes sold next. Okay? So this is how we interpret this number here. Now, there is a caveat to this, because it says in my explanation that we're going to earn $5 in profit for each pair of shoes sold next. That's not entirely true, because if I keep selling more and more and more shoes, then X is increasing. So now if I sell 20,000 shoes, I've sold an additional 10,000 after this point in time. Remember, that 10,000 that we used in the first place was part of this derivation here. So if I get up to 20,000, that rate of profit is going to change as well. So this explanation here is really only good for sales that are near 10,000. And really what that is, that goes back to that other interpretation that I had given you of the tangent line to a graph, which is that the tangent line is a good approximation tool for the graph of our function, but only locally, only for values that are near whatever we used to come up with that tangent line. Okay? Okay. A couple more examples. I think I'm going to wrap this up in one last video. So let's stop this one here.